A solid generally retains its shape, and whatever shape that is, it'll stay that way. It can be described by a single velocity for its center of mass, and some kind of rotation that defines how it's rotating around that center of mass. All of the individual components of that solid stay in the same relationship to each other as it rotates and translates along its path. A fluid, on the other hand, can start off in a particular shape, configuration, and with applied forces it will deform. And unlike a solid, as long as those forces are applied, it will continue to deform into different shapes. The result is that the individual little components of that initial blob of fluid don't maintain the same relationship to each other in space. It can't be described with a single velocity because each of these little components of fluid has its own velocity. And as a result, we need to define the velocity of the fluid in terms of field variables. So the velocity, u, is some function of where we're looking in space. So if we have a coordinate system, x and y and z, the velocity will be a function of where that particle is located, x, y, and z in space, and it may change with time. The forces that are applied in space are going to be the pressure forces, which are also a function of location and time, and viscous friction forces, which are also a function of position, location and time. Now those viscous forces depend directly on the velocity, and we'll get into that in more detail later. But the key thing to remember is to start off with simple fluid mechanics, we need to resolve what's going on with the velocity in the 3 dimensions of space and time and the pressure in 3 dimensions of space and time. For introductory fluid mechanics, we'll treat the temperature as isothermal and the density as incompressible, so that they will both be constant.